Imagine for a second the year is 1707. You're on the deck of a huge warship, maybe 90 guns, out in the middle of the North Atlantic.
Okay.
It's night. The fog is just this thick, wet blanket. You can barely see the front of your own ship, and the wind is howling.
And you've been at sea for weeks?
Weeks, maybe months. Now, you have a pretty good idea of your latitude, how far north or south you are. That part's okay. You could measure the sun's height or the North Star when the sky was clear.
But east or west? Your longitude?
You have absolutely no idea.
You are, for all intents and purposes, completely and utterly lost.
And being lost back then wasn't, just an inconvenience. It wasn't your GPS recalculating. It was terrifying. It was potentially a death sentence.
It really was the defining technological terror of the age of sail. You have these huge empires, Britain, France, Spain, building these global networks.
Right, with these massive navies.
Massive navies, sprawling merchant fleets.
Yeah.
And yet, the second they lost sight of land, they were essentially flying blind. It's an incredible paradox.
They could build these floating fortresses, but they couldn't answer the most basic question. Where are we?
Not with any real certainty, no.
And that's what we're diving into today, the solution to that one question. And it's not just a story about clocks and astronomy. It's a story about a working-class carpenter who basically took on the entire scientific establishment of Europe.
It's a clash of titans, really. The astronomers, with their celestial charts and complex mathematics.
Versus the mechanic.
Yeah.
The tinkerer in his workshop. We are talking about the longitude problem.
Which was, without exaggeration, called the greatest scientific challenge of the 18th century. It stumped some of the greatest minds in history.
Galileo tried to solve it.
Isaac Newton famously thought a mechanical solution was impossible. And in the meantime, it killed thousands upon thousands of sailors.
So let's lay the groundwork properly. To really get why this was such a monster of a problem, we have to understand the difference between latitude and longitude.
Right. Latitude, as you said, was, well, I wouldn't say easy, but it was a solved problem.
Why was it so much easier?
Because nature gives you these perfect, fixed reference points. The Earth spins on an axis, right? So you have a North Pole and a South Pole.
Fixed points.
Exactly. If you're in the Northern Hemisphere, you just find Polaris, the North Star. The angle of that star above the horizon is, give or take, your latitude.
So if it's 50 degrees up, I'm at 50 degrees north. Simple geometry.
Pretty much. Even in the daytime, you can use a sextant to measure the sun's highest point in the sky. That's your local noon. And with a simple chart, you can figure out your latitude from that.
So north-south is sorted, but longitude, that's the beast.
Longitude is the beast because the Earth is constantly spinning. There's no east pole or west pole in the sky to measure from.
Everything is moving.
Everything's moving from your perspective.
Yeah.
The sun, the moon, the stars, they all rise in the east and set in the west. There's no fixed celestial anchor for your east-west position.
Which means you can't just look up and measure an angle like you can for latitude. To find your longitude, you have to measure something else entirely.
You have to measure time.
Time. It's so fundamental. Longitude and time are basically the same thing.
They are two sides of the same coin.
We're absolutely going to unpack how that works because it's the key to this whole story. But before we get into the theory, I want to talk about the catalyst, the event that made this an urgent national crisis.
The tragedy that forced the government to finally act.
We're talking about Admiral Sir Cloudesley Shovel, October 22nd, 1707.
The Scilly naval disaster. It's a name that should be as famous as the Titanic, really, in terms of its impact.
And Shovel wasn't some minor figure. He was a national hero, a celebrity admiral. He's commanding this huge fleet, sailing back from the Mediterranean.
Returning from a long campaign against the French at Toulon. They're tired, they're heading home, they want to get to Portsmouth.
But the weather has been just atrocious for days on end. Vicious gales, fog, rain. You can't see the sun, you can't see the stars.
Which means no astronomical fixes. No way to calculate your latitude for days. So you're forced to rely on one thing and one thing only. Dead reckoning.
Which sounds as ominous as it is. Can you just break down what that actually involved? It wasn't just pure guesswork, was it?
No, it was a form of calculation, but it was based on a chain of estimations. First, you need your speed. You'd throw a piece of wood, a chip log, off the stern.
A literal log.
A literal log tied to a rope with knots tied in it at regular intervals. You'd have a sailor count how many knots passed through his hands in a set amount of time, measured by a little sand glass.
And that's where we get the term knots for speed at sea.
Well, that's exactly where it comes from. So now you have your speed. Then you check your compass for your heading. You multiply speed by time, and you get distance traveled in a certain direction.
So if I sailed north at 4 knots for 6 hours, I just pencil in on my chart that I've moved 24 nautical miles north.
In theory, yes. But that's a perfect world. What about ocean currents pushing you sideways that you can't see or feel? What if your compass has errors? What if the helmsman wasn't steering a perfect course? Every single one of those tiny errors, they add up. Hour after hour, day after day.
It's a cumulative error generator.
Perfectly put. And that's precisely what doomed Shovel's fleet. His navigators all got together on the flagship. They compared their logs, they debated their positions.
And they came to a consensus.
They did. They concluded they were safe, well west of the French coast, and were entering the broad, safe mouth of the English Channel.
They were tragically, horrifically wrong.
They had failed to account for a strong northwesterly current that had been pushing the entire fleet off course for days. They weren't where they thought they were. They were dozens of miles north and west of their charts.
They were heading straight for a place called the Isles of Scilly.
A vicious, notorious cluster of granite rocks and reefs just off the tip of Cornwall. A mariner's graveyard.
And in the dark, in the fog, they had no warning. At around 8 p.m., the flagship, HMS Association, slammed into the outer Gilstone Rock.
And a ship like that, a 90-gun behemoth, it doesn't just get a hole in it. The force of the impact on solid rock, it just disintegrated. Sources say it sank in less than 4 minutes.
Taking the entire crew, nearly 800 men with it.
And then the other ships, following their leader in the dark, sailed right into the same trap. HMS Eagle hit the rocks, then HMS Romney, then the Firebrand.
4 warships, just gone. The death toll is hard to pin down exactly, but it's staggering.
The best estimates are somewhere between 1,400 and 2,000 sailors drowned in a single night. One of the worst maritime disasters in the entire history of the Royal Navy.
And Admiral Shovel was among them. His body washed ashore the next day.
Yes, at a place called Porthilloch Cove. And this is where the story gets even darker, where it enters the realm of grim legend.
The story of the Emerald Ring.
The story of the ring. It's disputed by some historians, of course, but the legend is so powerful. It says that Shovel actually made it to the beach alive.
He survived the wreck.
He survived, but he was exhausted, barely conscious. A local woman found him lying on the sand. But she didn't see a hero. She saw the enormous, priceless emerald ring on his finger.
Oh, no.
And she wanted it. So the legend goes, she murdered him right there on the beach to steal it.
That's just a horrific image.
Yeah.
To survive that, only to be killed for a piece of jewelry.
The story gets wilder. They say that 30 years later, on her deathbed, she confessed to a priest and produced the ring as proof.
Wow. And there's another legend from that day, too, isn't there? The one about this sailor who tried to warn him?
Yes, the tale of the unnamed sailor, which feels almost like a folk tale about hubris. The story is that a common seaman on the flagship, a man who perhaps grew up on Scilly and knew the waters, went to the officers.
And he warned them.
He said their calculations were wrong. He could tell by the sound of the waves or the look of the water that they were dangerously close to the rocks.
And how was that received?
In the incredibly rigid hierarchy of an 18th century warship, for a common sailor to question the admiral's navigation, that was mutiny.
So what happened to him?
Legend says Shovel had him hanged from the yardarm on the spot.
Wow. So if that's true, the disaster wasn't just a tragedy, it was a kind of karmic retribution.
Whether it's true or not, it speaks to the immense pressure and the stakes. But the result was the same. The disaster sent shockwaves through the country. It wasn't just a loss of life. It was a national humiliation, a strategic vulnerability.
It proved, in the most brutal way possible, that the old methods were not good enough.
The merchants were screaming for the safety of their cargo. The Admiralty was screaming for the safety of its warships. And all that pressure led directly to one thing.
The Longitude Act of 1714.
Parliament's response. They basically decided to crowdsource the solution.
By offering an absolutely massive prize.
£20,000.
Which is hard to translate, but we're talking millions in today's money.
Depending on the metric you use, yeah, it could be 3, 4, maybe even £5 million. A life-changing, nation-changing sum of money.
And the requirements were incredibly specific and demanding. You had to find a method to determine longitude to within half a degree.
Half a degree of a great circle, which at the equator works out to about 30 nautical miles. And you had to prove it on a voyage to the West Indies and back.
30 miles? When ships were routinely missing their destinations by hundreds of miles.
It was an astronomical ask, pun intended.
Yeah.
They were asking for a level of precision that just didn't exist. And to judge all the proposals, They created the Board of Longitude.
Panel of experts.
And this is so important to the story. Look at who was on the board. The Astronomer Royal, the president of the Royal Society, professors of mathematics from Oxford and Cambridge.
The scientific elite, the establishment.
Exactly, and they were, by their very nature and training, astronomers and mathematicians. They looked to the heavens for answers. They were already predisposed to believe that the solution must be found in the stars.
Not in some grubby workshop.
Not with gears and springs. That was craft, not science, in their view.
Okay, so this brings us back to the core science of it. We said time equals distance. Let's really break that down, the orange segment theory.
It's such an elegant piece of logic. So you have the Earth, a sphere, 360 degrees.
Right.
And it rotates once every 24 hours. So you just divide 360 by 24?
You get 15. The Earth spins 15 degrees every hour.
Precisely. That's the magic number. So let's say you're a navigator. You need two pieces of information. You need to know the time where you are, and you need to know the time at a fixed reference point, like London.
Okay, so let's walk through it. I'm on my ship. Finding my local time is the easy part. I just watch the sun. When it reaches its absolute highest point in the sky, that's my local noon, 12 p.m.
Correct. Now imagine you had a magic docks on your ship, a perfect clock that you set to London time before you left, and it has kept perfect London time ever since.
So at the exact moment the sun is at its peak for me, I look at my magic box and it says it's 3:00 p.m. in London.
Right. So what does that tell you?
It tells me London is 3 hours ahead of me. The sun was at its peak over London 3 hours ago.
And since the Earth spins 15 degrees per hour?
3 hours times 15 degrees. 45 degrees. I'm 45 degrees west of London. I know my longitude.
That's it. That's the whole secret. The theory was understood for centuries. The problem was the magic box, the clock. Building a clock that could keep accurate time for months on end on a violently tossing ship through massive changes in temperature and humidity.
In the 1700s, that wasn't just hard, it was considered physically impossible.
Completely. We have to remember what clocks were like back then. There were pendulum clocks, beautiful, intricate things that worked by gravity.
A swinging weight. I mean, you put a grandfather clock on a ship in a storm.
It's useless. The pendulum will swing erratically or just stop. The motion of the ship makes it totally unreliable.
And that's just the motion. What about the environment?
Temperature was the big killer. All metals expand when they get hot and contract when they get cold. So the pendulum rod itself would physically change length between the cold North Atlantic and the hot Caribbean.
A longer pendulum swings slower, a shorter one swings faster.
So your clock is constantly speeding up and slowing down. It's useless for navigation. And that's before you even get to humidity rusting the parts and salt air turning the lubricating oil to sticky goo.
Even Isaac Newton weighed in on this, right?
He did. Sir Isaac Newton, as member of the board, stated flatly that a mechanical timekeeper for use at sea was an impossibility. The forces of nature were just too great to be overcome by springs and wheels.
So with the door seemingly slammed shut on a mechanical solution, the academic establishment focused all its energy on the other great hope.
The lunar distance method.
The astronomical solution. How on earth was that supposed to work?
The thinking was, if you can't carry a perfect clock with you, you have to use the clock that's already in the sky.
The moon.
The moon. It moves fairly quickly against the backdrop of the fixed stars. It travels about its own diameter, roughly half a degree every hour.
So the moon is like the hour hand of a giant celestial clock?
That's the perfect analogy. And the stars are the numbers on the clock face. The idea was that astronomers, back at the Greenwich Observatory, could spend years meticulously charting the exact predicted position of the moon relative to certain bright stars for every single hour of every single night.
And they'd publish this in a big book of tables.
Exactly. An almanac or an ephemeris. So the navigator at sea would use his sextant to measure the precise angular distance between the edge of the moon and a specific star.
Then he looks up that exact angle in his book.
And the book tells him, at the moment that angle occurred, the time in Greenwich was 9:47 p.m. He compares that to his local time, and boom, he has his longitude.
That sounds incredibly difficult.
It was a nightmare in practice. First, just taking that measurement on the deck of a rolling ship, trying to hold two moving objects steady in your sight. It was an art form.
And the sky isn't a perfect vacuum.
Not at all. You have to correct for parallax, the fact that the moon looks to be in a slightly different position depending on where you're standing on Earth.
Yeah.
You have to correct for atmospheric refraction, which bends the light.
So you take your measurement, and then you have to sit down and do a ton of math.
Very complicated math. We're talking spherical trigonometry. It could take a skilled navigator up to 4 hours of solid calculation to get one single longitude reading.
4 hours. In 4 hours, the ship has moved dozens of miles. By the time you know where you were, you're not there anymore.
Precisely. But to the Board of Longitude, this was elegant. This was science. It was based on the immutable laws of the cosmos. It felt proper.
Enter John Harrison, the man who didn't care about proper. He cared about what worked.
Harrison is the ultimate underdog in this story. He's not an astronomer, not a mathematician, not a member of the Royal Society. He's a carpenter from a small village in Yorkshire.
Largely self-taught.
Almost entirely self-taught. But he had this intuitive genius for understanding materials, for understanding friction and motion.
And he started out building clocks, but not normal clocks.
He built these incredible clocks made almost entirely out of wood.
Wood? Why wood?
He used a specific type of wood called lignum vitae. It's a tropical hardwood that is so dense and oily that it's naturally self-lubricating.
So his wooden gears and bearings wouldn't need oil.
Which means the oil could never gum up or freeze or get ruined by humidity. It was a brilliant solution to a centuries-old problem coming from a carpenter's perspective.
But that was just the start. He then tackled the temperature problem head on.
With his most famous early invention, the gridiron pendulum.
The gridiron.
This is just pure genius. He knew that different metals expand at different rates. Brass expands more than steel when it gets hot.
Right.
So he built a pendulum that wasn't one single rod. It was a grid of interwoven brass and steel rods. He arranged them in such a clever way that as the brass rods expanded downwards with heat, they made the steel rods expand upwards.
So the two expansions canceled each other out?
Perfectly. The effective length of the pendulum, the bit that determines the timing, never changed, no matter how hot or cold it got.
He literally hacked the laws of thermodynamics.
He did, and his land-based clocks were the most accurate in the world at the time. But the sea was a whole different challenge.
Which brings us to his first attempt at a marine timekeeper. The machine we call H1.
He unveils it in 1735, and it is a monster. It weighs over 75 pounds. It's this beautiful, intimidating contraption of gleaming brass with gears and springs all visible inside a case.
And it doesn't have a pendulum.
No pendulum. Instead, he designed these two huge interconnected dumbbell-shaped balances that would swing back and forth in opposition to each other.
So as one swings left, the other swings right.
Exactly. The idea was that the roll of the ship would affect both of them equally, but in opposite directions, so the errors would cancel each other out. It was a way to make a clock that was independent of gravity and motion.
And he had another key innovation inside it, right? The grasshopper escapement.
The grasshopper.
Yeah.
Best name for a mechanism ever. An escapement is the part of the clock that ticks, releasing the power from the gears in tiny, regular bursts.
The part that makes the sound.
Yes. And in every clock before Harrison, the escapement worked by sliding friction, metal pallets sliding against the gear teeth.
Which creates wear and needs oil.
And Harrison hated friction and oil. So he designed an escapement where the pallets didn't slide. They were on these little wooden arms that would engage with the gear tooth and then sort of hop off cleanly, almost like a grasshopper's leg.
So it was nearly frictionless?
And virtually silent. A masterpiece of mechanics.
So he takes H1 on a sea trial to Lisbon. How did it do?
It did pretty well. But the real proof came on the return journey. The ship's official navigator, using his dead reckoning, calculated that they were nearing the English coast at a place called the Start.
But Harrison checked his clock.
He checked H1, did his calculations, and said, "No, you're wrong. We're actually 60 miles west of there. We're about to hit the Lizard."
A much more dangerous part of the coast.
Very dangerous. But the captain trusted Harrison's machine, changed course, and sure enough, they sighted the Lizard Peninsula, exactly where H1 predicted it would be.
He saved the ship.
He had proven the concept. But the Board of Longitude, they weren't convinced. It wasn't accurate enough for the full prize. So they gave him some money to keep working.
And he builds H2.
H2 is even bigger, even more robust. And here, he introduces another brilliant idea called a remontoir.
Okay, what's that?
The problem with a mainspring in a clock is that it delivers a lot of force when it's fully wound and much less force when it's nearly unwound.
Right, that changing force would make the clock run at different speeds.
So the repertoire is a small secondary spring that sits right next to the escapement. The big mainspring rewinds this little spring every 30 seconds or so. This means the escapement is always getting its energy from this little spring that is always at the same tension. It gets a perfectly constant, even pulse of power.
That's incredibly clever. But H2 never actually went to sea.
It didn't. Harrison was his own worst critic, a perfectionist. He was testing it on land, and he discovered what he saw as a fatal flaw in the design. He realized that if the ship turned sharply, a motion called yawing, the forces could throw his big balances out of sync.
So he just abandoned it.
He abandoned years of work and started all over again on H3.
And H3. This one is the epic. This is his life's work, almost.
It really is. He worked on H3 for 19 years.
19 years on one machine.
From 1740 to 1759. Think about that dedication. He poured everything into it. He invented the bimetallic strip for H3, fusing a strip of brass and steel together.
I think I know this one. It's used in old thermostats, right?
Exactly, the same technology. Because brass expands more than steel, the strip bends when it gets warm. He used that bending motion to automatically adjust the balance spring to compensate for temperature. He also invented caged roller bearings to reduce friction even further.
He's just inventing key parts of modern engineering as side projects for this clock.
He is. But the clock itself, H3, he eventually had to admit it was a dead end. It was too complex, too big. He could never get it to be quite accurate enough to conquer the motion of the sea.
So here he is. He's an old man. He spent decades on these massive machines, and it looks like he's failed. The astronomers, led by a man named Nevil Maskelyne, are getting better and better with their lunar tables.
He looks like the astronomical method is going to win. The establishment is going to be proven right.
And then Harrison has a flash of insight. He has a complete paradigm shift.
He does. He'd had a watchmaker build him a personal pocket watch, but to his own advanced design. And as he was studying it, he realized something that went against all his previous thinking.
He'd been building bigger and bigger machines, thinking bigger meant more stable.
Right. A huge, heavy machine should be less affected by the ship's motion. But he realized that there's another kind of stability, the stability of high momentum.
Like a spinning top.
Exactly like a spinning top. A small, lightweight top, when it's spinning really, really fast, is incredibly stable. It resists being knocked over. It has high angular momentum.
So if he could build a watch with a balance wheel that was small but oscillated incredibly fast.
It would create its own stability. The tiny, rapid vibrations of the balance wheel would be too fast to be disturbed by the slow, lumbering roll of a ship.
So he abandons the huge sea clocks.
Abandons 30 years of work on that concept and pours all his genius into a new machine. H4. It looks like a very large silver pocket watch, about 5 inches in diameter, beautifully made. But inside is a revolution. The balance wheel beats at 5 beats per second. Incredibly fast for the time.
Creating that stable, humming heartbeat that the ocean couldn't stop.
That was the theory.
And in 1761, it's time for the ultimate test. H4 is sent on a voyage to Jamaica on the warship HMS Deptford.
Harrison himself is now in his late 60s, too frail to make the voyage. So his son, William, goes in his place to look after the watch.
This is it, the culmination of his entire life.
81 days at sea, they cross the Atlantic, they arrive in Jamaica. The local time is confirmed by astronomers on the island. They check the time on H4, which has been ticking away in its box for the whole voyage.
And the result?
After 81 days at sea, tossed around on a wooden ship through storms and calms, H4 had lost a total of 5 seconds.
5 seconds.
5 seconds.
Almost 3 months.
It's a level of accuracy that is just mind-boggling. It equated to an error in longitude of just 1.25 minutes of arc.
Which is about 1 nautical mile.
1 mile. The prize required an accuracy of 30 miles. Harrison hadn't just met the standard, he had shattered it. Obliterated it.
So this is the happy ending, right? He goes back to the Board of Longitude, they verify the results, they hand him a giant check, and he retires a national hero.
You would think so. But this is where the story turns from a tale of invention into a tale of politics and professional jealousy.
The Board of Longitude was not happy.
The board, and specifically its new powerful leader, the astronomer Royal Nevil Maskelyne, was not happy at all.
This is a huge conflict of interest, right? Maskelyne is the chief judge of the competition, but he's also the chief advocate for the rival method.
A massive conflict of interest. And to be fair to Maskelyne, he probably wasn't just being a villain for the sake of it. He genuinely believed that the lunar method was intellectually and practically superior.
What was his argument?
He saw Harrison's watch as a one-off. A fragile, incredibly complex, and expensive little toy made by a singular genius. His question was, is this a real solution for an entire navy? Can you mass-produce these things? Or did Harrison just get lucky? Is it reproducible?
Which is, I suppose, a valid scientific question.
It is a valid question. But Maskelyne used that question as a weapon to deny Harrison his prize. The board said the result might have been a fluke. They demanded a second trial.
So Harrison agrees to a second trial.
He does. H4 performs brilliantly again. And the board still refuses to pay. They start adding new conditions. They demand that Harrison hand over all his technical drawings. They demand that he completely dismantle H4 in front of a committee of watchmakers and explain how every single part works.
He has to give away all his secrets.
Every single one. And then came the ultimate insult, the unsprung cart incident.
This is just awful.
The board demanded that all 4 of Harrison's timekeepers, H1, H2, H3, and H4, be handed over to them and taken to the Royal Observatory at Greenwich for testing.
And Maskelyne is in charge at Greenwich.
Maskelyne is in charge. He sends some men to Harrison's house. And Harrison, now a frail old man, has to watch as they load his entire life's work, these incredibly delicate precision instruments,
into a cart with no springs,
and haul them over the rough cobblestone streets of London. H1 was apparently dropped on the floor before it even got out the door. It feels deliberately punitive.
like they wanted to damage them.
It's hard to see it any other way. And when the clocks got to Greenwich, Maskelyne subjected them to a testing process that seemed perfectly designed to make them fail. He'd leave them in a cold draft, then in direct sunlight. He wouldn't wind them correctly.
And then he published a report saying they were unreliable.
Of course. And in the meantime, Maskelyne publishes the first edition of his nautical almanac, the official tables for the lunar distance method, and gets the Navy to adopt it. He was winning the political war.
So Harrison is at the end of his rope. He's done everything they asked. He's met the conditions of the act multiple times. The board just keeps moving the goalposts.
He's desperate, so he decides to go over their heads. He plays his last card. He appeals directly to the king.
King George III.
The very same. Now, we often remember him as the mad king who lost America. But at this time, he was young, sharp, and a huge patron of science and technology. He had his own private observatory.
And Harrison gets an audience?
His son William does. He gets in to see the king and lays out the whole story. The decades of work, the successful trials, the board's endless obstruction.
And the king listened.
The king was apparently outraged. He is reported to have said, "By God, Harrison, I will see you write it."
And he didn't just say it, he took action.
He did. Harrison, in his old age, had built one final timekeeper, H5, a copy of his masterpiece. The king said, "Forget the board, bring it to me, I will test it myself."
So the King of England personally tested the watch.
For 10 weeks, at his private observatory in Kew, he logged its performance every single day. The result: H5 was accurate to within 1/3 of a second per day.
That is just unbelievable precision.
It's approaching modern quartz accuracy. The king was convinced. He went to his prime minister, Lord North, and basically threatened to go to Parliament and publicly shame them if they didn't pay Harrison what he was owed.
And that royal pressure finally worked.
It did. In 1773, Parliament voted to give Harrison a final payment, which, when added to the sums he already received, finally equaled the prize money, a total of over £23,000.
So in the end, he got the money.
He got the money. But here's the bitter twist. The Board of Longitude never, ever officially declared him the winner of the prize.
Seriously?
They never conceded defeat. Technically, the prize was never awarded. Harrison got his money through Parliament, not the board. He died just 3 years later.
But history has a way of deciding the winner, doesn't it?
It certainly does. For a while, the two methods coexisted. Smart captains would carry a chronometer and use the lunar method to double-check it.
But the lunar method was still slow and hard.
And prone to mathematical errors. Meanwhile, other brilliant watchmakers like Thomas Earnshaw and John Arnold took Harrison's designs, simplified them, and figured out how to mass-produce reliable, affordable marine chronometers.
So the chronometer won?
It became the absolute heart of the ship. By the 19th century, every naval vessel, every merchant ship had one. It was kept in a gimbaled box, protected like a sacred object. It gave the British Navy a massive navigational advantage and helped build an empire.
And the legacy of this whole struggle is something we still live with every single day. The prime meridian.
Absolutely. Because it was the British who solved the problem. with both Harrison's chronometer and Maskelyne's almanac. All the best and most accurate charts in the world were based on London, specifically on the Royal Observatory at Greenwich.
Other countries had their own zero-degree lines, right? The French used Paris.
They did. But British maritime power meant their charts became the de facto international standard. So in 1884, when all the nations got together to finally agree on a single prime meridian for the whole world,
They chose Greenwich.
they voted to make the line passing through the observatory at Greenwich longitude 0. All because a Yorkshire carpenter built a perfect clock.
If a Frenchman had done it, we'd all be setting our watches to Paris meantime.
Very, very likely.
So eventually, what replaced the mechanical chronometer, it wasn't used forever.
No, technology moves on. The next big leap came in the early 20th century with the invention of wireless radio.
Time signals.
Exactly. Suddenly, you could broadcast a precise time signal from a powerful transmitter on land, like the Eiffel Tower.
So a ship out in the middle of the Atlantic could tune in at a certain time, hear the beep, and reset their chronometer.
Or at least check its error. It took away the problem of the clock's accumulated drift over a long voyage. And that system lasted for decades until the final evolution,
GPS.
the global positioning system, which, when you boil it down, is just John Harrison's principle taken to its ultimate conclusion.
It's still just a clock.
It's just a constellation of satellites, each one carrying an incredibly precise atomic clock. Your phone, or your ship's receiver, listens for the signals from several of these satellites.
And it measures the time it takes for the signal to arrive.
Down to the nanosecond. And since it knows the speed of light, which is constant, it can convert that travel time directly into distance.
Time equals distance.
It is the exact same idea, just with cesium atoms instead of brass wheels and satellites instead of the sun.
It is incredible to think that the little blue dot on your phone map is the direct descendant of a shipwreck off the Isles of Scilly 300 years ago.
It's an unbroken line of technological development.
You know, what really strikes me about this whole deep dive is the nature of where the breakthrough came from. You had the establishment, big science, the Royal Society, the astronomers, the universities.
They had the prestige, the funding, the government backing.
And they had a solution that was elegant and academic and deeply impractical.
For the everyday user, yes.
And the real solution, the one that actually changed the world, came from a guy in a workshop. A man covered in sawdust and metal filings who just refused to give up.
The quintessential garage tinkerer. Harrison didn't have Newton's grasp of theoretical physics. He had an intuitive physical grasp of how things worked, and he was dismissed for it. He was seen as an annoyance, a craftsman, not a true scientist.
Which really makes you think about today. We have our own modern boards of longitude, huge tech corporations, government research grants, the established scientific consensus on certain issues.
And we have our own seemingly impossible problems. Sustainable energy, curing certain diseases, true artificial intelligence.
So the final thought I want to leave you with is this. Who are the John Harrisons of our time? Who's out there in a basement or a garage somewhere working on a solution that looks too simple or too mechanical or just too strange for the experts in the field to take seriously?
And are we making the same mistake the Board of Longitude did by dismissing them out of hand?
It's a humbling question. The next world-changing idea might not come from a grand institution.
It might be ticking away right now in a box in someone's workshop.
That's all for this deep dive into the clockwork ocean. Thanks for joining us.